Hi there, Mr. Sutton here, bringing you the Algebra 2 5-7 lesson on inverse of a function. In this one, we will be finding and graphing inverses of a variety of functions. And if you're doing the honors version of this lesson, we're also going to be verifying that functions are inverses, among some other interesting things. So to kick this one off, let's talk about Star Wars, because why not? So, like the Force in Star Wars, mathematics is balanced. We've got pairs of functions and operations that you've probably seen undo each other. So just to start things off here, pause the video and list as many pairs of undoing operations as you can think of. Just think about when you're solving an equation and you have to undo something, what do you undo it with? All right, so some of the more common pairs that you're used to, we've got addition and subtraction. And then in the kind of the same breath, we've also got multiplication and division. So these are kind of the big four, but there's some other ones you've encountered as well. When we had to solve quadratic equations, we used square roots. And when we had to solve cubic equations, we sometimes used cube roots. In general, we can use an nth root to undo an nth power and vice versa. Now there's a few others that are we haven't encountered yet this year, but we will. So all of the trigonometric functions have inverses. Sine, which you may remember in past years if you did SOHCAHTOA, sine has its own inverse function, which we could either call sine inverse or arcsine, and all the other trig functions have versions of this as well. We're going to do later on this year logarithms and exponential functions. So it turns out log base b of x and b to the x also undo each other, although that probably doesn't make a whole lot of sense just yet. Just planting the seeds for later. And another one that we'll throw in there that we could use more or less immediately is x to the negative 1 and, interestingly, itself, x to the negative 1. When you raise something to the negative 1 power, you get the reciprocal. And if you take the reciprocal of a reciprocal, then you should get what you started with. So these are all sort of undoing sort of functions, feeding into this idea of what we call inverse functions. So let's talk a little bit more explicitly about inverse functions now. Inverse functions, and the notation on this, there's a little negative 1 exponent next to the function name to indicate that it's an inverse. This is not reciprocal, this is actually inverse, f inverse. An inverse function undoes another function. Again, like addition and subtraction, those are inverse functions. But the ones we're talking about are going to be a little more complex than just a one-step sort of inverse. So to dive a little bit deeper into what these inverses are doing, an inverse function takes the output from the original function and returns the original input. So instead of taking an x and giving back a y, we're essentially taking a y value and giving back an x. In terms of the points that are on the function, we're basically switching all of the x and y values. So if the point 1, 2 was on the original function, now the point 2, 1 is on the inverse function. It's kind of a direct mapping like that. And just graphically, while we're talking about points, we're basically reflecting the original function over the line y equals x. And this kind of makes sense because if we're switching all the x and y values, then the line y equals x probably is going to be involved somehow. So this is kind of nice to have this idea of a function that can undo another function and get back to the original input. Kind of a good application of this would be like if you encoded a message using one function, being able to plug in the encrypted message into an inverse function and get the original message back would be kind of nice. So the next question is, do all functions have inverses? Well, for that we need a concept of something called a one-to-one function. This is a function where every x returns one and only one unique y value. So in other words, there's no repeat x's and there's no repeat y's. So if I plug in two different x values, I will get back two different y values. So remember when we were talking about functions, we said that we're not allowed to get two different y values back. Well, this is kind of more strict than that. This is saying we're not allowed to plug in two different x values and get the same y value back. Now, the reason this is important is that one-to-one functions and only one-to-one functions have inverses that will also be functions. And if you think about why this has to be the case, let's say we had a function that did give us a single y value for two different x values. If I turned around and plugged in that y value to find out the original x value, but there were two x values that could give me that y value, well, then I wouldn't be able to tell which x value I was supposed to give back. So we need a one-to-one function to make this work. So functions that will give you the same y value for different x's, therefore, are not going to have an inverse function, at least not in their original form. Some examples of this that you might remember: if you have x squared, because negatives and positives both become positive when you plug it in there. And kind of along the same lines, the absolute value function has this problem as well. Sine and cosine, we're going to see later on, have multiple inputs that will give you the same y value. They actually look like waves, so you're actually repeating over and over again. It's not just a positive versus negative thing. And another common case that I like to throw in there is a constant function. If you have a horizontal line where literally every input gives you the same output. So these all fail something called the horizontal line test, which basically means if you draw a horizontal line and it touches the function twice, that means it's not going to have an inverse that's a function. This is just kind of a quick graphical way of checking to see if you're getting the same y value from different x values. Now, before you get all sad that x squared, absolute value, sine, cosine, and all these others cannot have inverses, it turns out there's a little workaround for this. These functions can have inverses if we restrict their domains so that we're only plugging in certain x values, and then if we make some kind of inverse out of it, we'll only be able to get those x values back. With that theoretical understanding in mind, we're going to try to find our first inverse of this function. It's just a linear function. And after we find that, we're going to use Desmos to actually graph it out. So first step we need to do, since an inverse switches all the x's and y's, we literally need to switch x and y. And if you're like, well, where's the y? Well, that's just this f of x right here is really y. So we're going to replace f of x with x, and we're going to replace this x over here with y. So x equals 3y minus 1. And then to make it an inverse function, we're just going to solve for the y. And when we get y by itself, we're going to rewrite the y as f inverse of x, f with that little negative 1 up there. That makes it official. So pause the video and see if you can take it the rest of the way on the algebra part here. All right, so our next step, if we're getting y by itself, just add the 1 to the other side, so just normal kind of equation solving rules. And then to really get y by itself, we need to divide by 3. So we've got y equals x plus 1 over 3. Only we're going to be fancy and call this f inverse of x equals x plus 1 over 3. All right, so at this point, we are going to graph this out. Now, one thing you can do to see if you actually have the inverse, before we do anything else, you can always check by plugging a number into the original function, getting an output, and then plugging the output into the inverse to see if you get the input back. So if we take an easy thing like, let's plug in 2, 3 times 2 minus 1 would be 5. And if we plug 5 in here, 5 plus 1 over 3 would give us back the 2 that we started with. So that's a quick way to check. All right, so graphing this out, we're going to graph the original f of x and the inverse on Desmos on the same axes. When we do this, though, we're going to have to rename this f inverse as something else, like g or h, whatever you want. Unfortunately, Desmos doesn't really recognize this sort of notation here. All right, so here we are on Desmos. Let me do f of x equals 3x minus 1. So there's the original line, which we didn't really need Desmos to graph it, but we're sort of getting used to this Desmos stuff. Then let's go down here, and I'm going to rewrite this inverse function as the g function. So g of x equals, let me do a fraction, x plus 1 divided by 3. And to see that this is really the inverse, remember inverse means it's reflected over the line y equals x. So we're going to actually graph y equals x along with these other things and see if we have a true reflection. So going back in here, let me do another function now. We'll just do y equals x. And if you want to be super fancy, you can do this little gear thing and click on this one, and you can change your line to be dashed if you like. Super fancy now. And we see that the two things that we graphed are reflections of each other over this line. So that's pretty cool. Now there is one other neat little thing. So here's everything that we graphed just to get it all out there. So on Desmos, if you want to directly graph an inverse, you can just write x equals f of y once you've already defined the f of x function. So let me just show you that coolness here. So let me unselect my inverse here. And now let me just write x equals f of y. And there it is again. That's the inverse. So here is the other inverse we have. It's the same function. So that's kind of neat too. Next up, we are going to find the inverse of a quadratic function. Now you might be thinking, hold on a sec. Quadratics, those take the different x values that are positive and negative and make them both the same positive y value. So you might be thinking, well, this thing doesn't have an inverse. This would fail the horizontal line test. Certainly, it's a parabola. But look here, we've got this domain restriction of x less than or equal to 0. So that's going to cause us to only have a single y value for each x value that we plug into this thing. So also one thing that's kind of weird on this one is at some point you're going to have to take a square root of both sides of an equation, and you're going to get initially kind of a plus or minus radical. So at that point, you're actually going to have to pick one of those signs for the radical. So we are going to use this domain restriction here to determine whether that plus or minus root is actually positive or negative. And the way this is going to work is if the domain restriction is only giving us x values that are to the left of the vertex, then we're going to have to go with the negative root. Kind of the negative goes with the negative here. If we have right of the vertex domain, then we would go with the positive root. So I know this is a little bit weird doing it for the first time, but pause the video and see if you can get the inverse function out of this. All right, so our first step is pretty straightforward. Again, we're just switching the x and the y. So we can write x equals 4 times y squared. And now isolating the y, we just divide both sides by 4. And we're going to square root both sides. Now again, when we square root an equation, we end up with a plus or minus. Because this domain restriction is making us get values that are to the left of the vertex is at 0, 0 for this thing, that means we're going to pick the negative square root to kind of duplicate that. Part of the reason that this is going on here is that the domain of the original function is going to become the range of the new function. So that means if your domain, in this case, is giving you negative values, your range is also going to have to give you the same sort of negative values. So we have y equaling the negative root of x over 4. And then we can simplify that a little bit to be negative radical x over just plain old 2. All right, so let's go ahead and graph these out now on Desmos. So we have our original function, f of x equals 4x squared. And we also have g of x, now for the inverse, equals negative square root of x, and we'll divide all of that by 2. And here's, let's also do the y equals x line there. We don't need to make it dashed, it doesn't really matter. All right, so this looks kind of weird because that parabola doesn't have its domain restricted yet. So as an extra little Desmos sort of trick you can do, if you want to restrict domain on Desmos, you have to do curly braces with the domain restriction next to the function that you're restricting. So in this case, we would do 4x squared and then curly brackets, x less than or equal to 0. So let me go back here and show you that. So this is this function here. Let me do a space, open a curly brace, and x we want less than or equal to. So I'll do less than, then type the equals, and it automatically makes it less than equal, and that was going to be 0. Close the curly brace if you want, and then notice that our parabola now only has a single branch to the left of the x-axis. So this is everything that went into making that gorgeous picture. Here's another quadratic for you to play with. Pause the video and see if you can go all the way with this one. All right, so let's start by first switching x and y. So we have x equals y minus 3 quantity squared. And again, this domain here is forcing us to only take one branch of the parabola, so we're not failing the horizontal line test. So next step, we have to square root both sides, and we're going to get either a plus or a minus radical x over here. Now, since this domain is taking all the stuff to the right of the vertex, plugging in things that are greater than or equal to 3 is going to give us positive numbers out of all this. That means that we need to take the positive square root so that we get a positive range out of all this. So this is going to be positive radical x equals y minus 3. And then we just add 3 to both sides, and we have f inverse equals radical x plus 3. All right, let's go to Desmos and graph all this out. So let me move this so I can see things. We have f of x equals parentheses x minus 3 squared, and then curly bracket x, let's see, we've got greater than or equal to 3. So that gives us the right branch of the parabola. And now for our inverse, we've got square root of x, get out of there, and then plus 3. And then let's just graph y equals x to make sure. Yep, that definitely looks like that is the inverse. So there we are. So we're going to up the ante a little bit. We did a quadratic equation just a moment ago. Now we're going to go up to a cubic equation. And I submit that you actually know everything you need to in order to do this one. So pause the video and give this a shot. All right, so we've got x equals 2y cubed plus 1. Solving for y, we have to first start by subtracting 1 from both sides. And then we'll divide both sides by 2, so that's x minus 1 over 2 equals y cubed. And then we have to take the cube root of both sides. Now remember, when you're taking an odd root, you don't do the plus or minus. That's only when you're doing even roots, like second root or fourth root or any of those. So this is just going to be f inverse equals cube root of x minus 1 over 2. Let's go to Desmos and graph this. So on Desmos, we have f of x equals 2x cubed plus 1, and g of x equals, now we'll do CBRT for cube root, and then do a fraction in there, x minus 1 over 2. And that sure looks like the inverse, but let's do our y equals x line. Yep, we've got the inverse. Awesome. And there it is again. All right, so our last type of function we're going to find an inverse for is a radical function here. So pause the video and try this one out. All right, so switching x and y, we've got x equals 2 radical y minus 3. We can divide both sides by 2 to get the radical by itself at least. And now we're going to have to square both sides. So that's going to be x over 2 quantity squared equaling y minus 3. And then let's just add 3 to the other side to get y by itself. So we have f inverse equals x over 2 squared plus 3. Or you could make that x squared over 4 if you want to simplify it a little bit. Beautiful. All right, so let's go ahead and graph this. So we have f of x equals 2 square root x minus 3. There's the original function. And now let me do my inverse. G of x equals, let's see, fraction. We got x squared over 4 plus 3. And let's do my y equals x line. Okay, now this is a little bit weird. This is not quite a true reflection. Like, part of it's a reflection, but then we have this piece over here that doesn't really have an analog going this way. So what's going on with that? So what's going on is that your original function actually only had a range of positive numbers, because square root can only return 0 or positive. But that range of the original becomes the domain of the inverse. So if you have a range of only positive numbers, your inverse is going to have a domain of only positive numbers. So in general, since the range of f is non-negative, the domain of f inverse has to be restricted as well. So we need to add a little stipulation on this f inverse that x is greater than or equal to 0. And part of the reason we have to add this as well is because it's not already built into this function. I mean, up here they didn't specify y greater than or equal to 0 because that's implied by the square root function. It's already built into it. X being positive, not built into the x squared function. So if we throw this into Desmos now, so we're going to go to our g function and we're going to add that little extra stipulation, x greater than equal to 0. Now we end up with something that truly mirrors the original function. And there it is. So at this point, if you are doing the CP non-honors version of this lesson, this is actually the end of the lesson for you. You can stop the video and try out some problems involving finding inverses and graphing them on Desmos. If you're doing the honors version, then this is just the end of part 1. We've got another part in store for you with some extra things, so stay tuned for that. Welcome back. If you're joining us for the honors version of this lesson, we're going to kick things off by finding another inverse, only this time we're going to do it graphically. And being able to find inverses graphically can be kind of handy, especially if the function that you have doesn't have like an algebraic function that goes with it, or at least a function that it's easy to switch x and y and solve for y. So if you can just do it on the graph, you can at least get a functional sort of picture to help you out. So the way we're going to do this, since an inverse we've seen over and over again is a reflection over the line y equals x, we are literally just going to pick some easy points on the original and reflect those over the line y equals x, and then connect the dots in a shape that vaguely resembles the original here. So pause the video and give that a shot. All right, let's see how that went for you. So I'm going to pick points that are clearly on grid lines to make it easier on myself. So I've got this point right here, the endpoint, and I'm also going to do -2, 0, and up here I think -1, 3 is another good point. Let me graph my y equals x line. It's just a line with a y-intercept of 0 and a slope of up 1 over 1. It's like the first line we ever learned to graph. And then let's reflect these over that line. So this first point is coming down here. This next point is going to be going, let's see here, this way. There we go. And this point, we're going 2 diagonals in and just keep going another 2 diagonals in the other direction. Now, the endpoint got reflected to this spot right here. So we're going to start here, and this is where our function is going to go through. For our next fancy advanced trick that we're going to do, we're going to figure out how to verify that two functions are inverses of each other. They might be, they might not be. Now, one way you could quickly test this out is just pick a number and plug it into one function, get an output, plug that into the other function, and see if you get the original input that you plugged in. So, for example, I could plug in, I don't know, let me pick 4. If I plug 4 in here, 3 times 4 is 12, minus 1 is 11. And then if I plug 11 in here, 11 plus 1 is 12, divided by 3 is 4. That was the original number I plugged in. So that's great. And you could do that for a bunch of numbers. And if you keep getting the same results, that kind of suggests that these are inverses, but it's not a rigorous proof. I could just be getting lucky, really lucky, each time with the numbers I'm picking that they just so happen to work out. To do this rigorously and have it stick beyond any shadow of a doubt, we need to actually do that process using x. So if I do f of g of x, I should get back just x, the original any number that was plugged in. By the same token, if I do g of f of x, I should just get back the original x. So this is really what we need to show. If f of g of x and g of f of x both equal x, that shows rigorously that f and g are inverses, and nobody can doubt our results. If we don't get those results otherwise, then that shows that these are not inverses. So pause the video and try that approach here, and let's find out if these are inverses. All right, so we'll start by doing f of g of x. So that's going to be f of x plus 1 over 3. That means we're doing 3 times x plus 1 over 3 minus 1. So this is just essentially composition of functions, which we've seen before, and here's a use of it. These 3's are going to cancel, so that's x plus 1 minus 1, and then that's just going to be x. So it works out this way. Now we do need to do the other direction, and if you're not sure why, then well, let's just do it and I'll explain after, all right? So let's do g of f of x. So that's going to be g of 3x minus 1. So that's going to be 3x minus 1 plus 1 all over 3. That's going to be 3x over 3 if we cancel out those 1's, and then 3x divided by 3 is just 3, or x rather. All right, so this proves that f and g are inverses. Now, you're probably wondering, if I already showed that I got x by doing f of g of x, why do I need to do the whole process over reversing the order of the functions? And there are some cases where you might do it one way and get x and the other way and get something different. Kind of the poster child for those oddball cases is x squared and radical x. So if you do the square root of x squared, then you get x. But if you do radical x and square that, you get x, but you get x with a domain that, because of the radical, is restricted to only positive numbers. So if you get x and x, but the domains are different, that doesn't count. So this is why you have to do both of these for weird cases like that. So at this point in the lesson, we're going to answer the question you might have had, which is, hey, these inverses are kind of neat, but what can I actually use them for in real life? Well, here's one possibility. Let's say that there's a student named Cody or whatever in your math class, and you want to ask them on a date. But before they can answer, I interrupt you and say, hey, it's not a talking time, get back to work. And Cody, being the clever student they are, slips you a note with their answer. Here's that note. So you see the following on this crumpled up piece of paper. We have some f of x function that is kind of crazy. It's a fifth root of x cubed minus 100. We have some random decimally sort of things going on here, and we have a table that correlates each letter of the alphabet with a number from 1 to 26. So you're looking at this and you're thinking, okay, let's assume that these 4 numbers were created by maybe taking 4 letters out of here, getting a number, assigning a number to them, and then plugging them into this function. So this function is giving us these 4 numbers based on 4 original numbers out of this table. If only we could figure out the original 4 numbers that were plugged in, that might help us decode this hidden message and see if we've got a date. So let's keep going on this one. So this problem is a clear case of in an inverse function being kind of helpful. I mean, one approach you could take is to plug all 26 numbers into this function and get kind of a new table, and then compare these numbers to that new table. But that's 26 plugins. It'd be much more efficient to just have a function that undoes just these 4 numbers and figure it out that way. So pause the video, see if you can get the inverse function, and if you're feeling ambitious, hey, maybe plug these in and decode that message. Give it a shot. All right, so let's start by swapping x and y. So we have x equals fifth root of y cubed minus 100. And then next thing I'll have to undo is this fifth root with the fifth power. So this is x to the fifth equals y cubed minus 100. Then we can add 100 to both sides. And then finally, if we take the cube root of both sides, we get f inverse. So cube root of x to the fifth plus 100. So at this point, let's go to Desmos and plug these numbers in and see what we get. So it's up to you on this one. I mean, we've been using the graphing calculator for the whole lesson, but you really only need the scientific calculator for this. So let me do g of x for my inverse equals cube root of x to the fifth plus 100. And let me go down now and start plugging things in. Now, one thing we'll need to keep in mind is that these were probably rounded off just based on the type of function that this is. So the numbers we get back may not be precisely what we see in the table, so we're just going to round it off to whatever they're closest to. So let's do g of 6.890 to start with, and that's roughly 25. So there we go. Let's next do f inverse of 1.903. So 1.903 comes out to roughly 5. And then f inverse of negative 2.507. Let's see, negative 2.507, and let's get rid of the rest of that. I think that's 1. That should be 1. Roughly 1. And then we'll do 3.334 as well. So 3.334, and that is pretty close to 8. So we have 25, 5, 1, and 8. 25 goes with Y, so that's a good one to start with. And then 5 is E, 1 is A, and then 8 is H. So yeah, hey, we got a date. Awesome. So that's it for this one. I will leave you and Cody to your fun-packed date. You can do your homework together. Until next time, Mr. Sutton signing off.